right. Wait, maybe one more minute. So you have your presentation. It's all working.
I think so. Can you see my cursor moving?
Yeah. Do you have this laser pointer effect?
No.
That would show it a little bit better.
No, I don't. Sorry.
Okay. We can live with that. Okay. So. Right. So it's a pleasure to host Frank Pollmann from TUM, Technical University of Munich. Frank did some really pioneering work, condensed matter, theory of condensed matter of strongly correlated systems, including works on classification of topological phases and many-body localization and many other things. And today he's going to tell us how to use quantum processors to do some cool stuff. Okay.
Thanks, Nate, for the kind introduction and for the invitation to give a seminar here. And as Nate pointed out, I'm going to talk about some ideas of using quantum processors, or to be more precise, some near-term quantum devices for studying emergent many-body physics. And the work that I'm showing today has been done together with two students, Leo and Bernard, in my group in Munich, together with a postdoc, Adam, who just recently moved from France to Nottingham, my colleague Michael Knapp, Andrew Green from the University College of London, Christina Knapp at Microsoft, and two experimental colleagues at Google, Kevin and Petra. Yeah, also please feel free to interrupt me at any time if something is not clear. So let me, before discussing quantum computing, talk a little bit about the kind of questions that I want to address using quantum computers. So we all very much aware of the fact that the matter surrounding us occurs in various different phases, and commonly we distinguish different phases of matter in terms of spontaneous symmetry breaking. Right? So water ice, for example, spontaneously breaks the continuous rotation symmetry of sprays. However, over the past couple of decades, many new phases, conceptually new phases of matter have been discovered where this framework does not apply. So these are the ideas where we have well-defined quantum phases of matter that cannot be distinguished by any local order parameter and not by spontaneous symmetry breaking. And here I'm giving that some sort of an incomplete list of different phases of matter. So these would include symmetry-protected topological phases. These are phases of matter that do require certain symmetries to be well-defined, but yet they wouldn't break it spontaneously. There's sort of intrinsic topological order. These systems do not require any symmetries in the system to distinguish different topologically ordered phases. And there are also some rather exotic new phases, so-called fracton phases, which I'm not going to talk about in this talk. And the main scheme, or the main idea that I want to follow in this talk, is that we have now what's called these kind of noisy intermediate scale quantum devices. So these are quantum devices which operate at a quantum level, so they can entangle many qubits, but that happens in a very noisy way. So we don't have long-lived, well-defined sort of logical qubits. And the question is, like, how can we now use these machines to investigate this kind of physics and phase transitions between different topological phases? To be a bit more precise, is that if we want to, for example, investigate a certain model Hamiltonian, and we want to figure out whether the ground state of this particular model Hamiltonian, describing, for example, a spin 1/2 system on some lattice, has a particular topological order or not, or if we tune a particular Hamiltonian, what are the universal property of a particular type of phase transition. These are problems that we often address using, for example, exact diagonalization, where we would completely diagonalize the Hamiltonian or find the exact ground state numerically, and then we just analyze the properties of the ground state wave function. The problem is that solving this problem on a classical computer scales exponential. And just to put some numbers on it, if we take, for example, some frustrated lattice of about 40 or so spins, this is what we can still do using some of the largest computers available. If we want to use a few more spins, then of course we have to double or quadruple the number of cores, which is very quickly not possible anymore. And now the hope, at least this is the hope of many, is that the newly designed quantum computers that already now have the order of 50 and more qubits could be of great help, right? Because the state-of-the-art quantum devices already have way more qubits than what could be simulated on classical computers. However, this number is a bit deceptive because it raises the hope that you can do whatever you can do on a classical computer with these kind of 50 qubits, which would be great, but this is not the case. So there are 50 or even like up to 100 qubits. However, what you can do with them is very limited. It's limited in terms of the circuit depth, right? So basically the length of the programs that we... So is there a question?
I think it's just unmuted participants.
Okay, sorry.
We take care of that for you.
So, right, so we have these already rather high number of qubits, but what we can do with them is strongly limited because of these machines being rather noisy. And what I am interested in right now is what kind of problems are hard on classical computers, but might be doable on some near-term NISQ devices, right? So basically just to identify some wedge of problems, a certain set of problems where we can enjoy some quantum advantage on near-term devices. And I want to discuss two projects that we did recently and on exactly this question. The first one is that I want to demonstrate some idea how we can study so-called symmetry-protected topological phases on quantum computers and investigate also transitions between different SPT phases. And the second part, I want to discuss how quantum computers can be used to investigate genuine kind of topologically ordered states. So let me start with the first part and again provide first a little bit of background and let me just first again define what we refer to as a gapped quantum phase of matter. So we are now interested in the physics at zero temperature. So we are just interested in ground state properties of a given Hamiltonian. And I want to think of a phase of matter as basically some equivalence class. So I would say that two Hamiltonians are in the same phase if I can find some continuous path connecting those two without closing the gap or without any singularity in the ground state wave function. Right? So for example, I just have some Hamiltonian H0 and Hamiltonian H1, and now I find a continuous parameter going from one to the other. And if I can do this without encountering any singularity, then I define those to be in the same phase. On the contrary, I'm saying that H0 and H1 are in different phases if there is some unavoidable gap closing or like some unavoidable phase transition or singularity, right? So and then I have to decide about by what rules I apply to this path. And for certain cases, for example, for the symmetry-protected topological phases, I'm talking only about paths that obey certain symmetries. Right? Now, in one-dimensional systems, there exists a complete classification of these phases. So basically, I can just come up with a certain set of labels, and then I can just tell if a given system or given state is in the same phase as another state. So there are two different ways how we can distinguish phases in one dimensions. The first one is that a ground state of a Hamiltonian spontaneously breaks the symmetry. So as a prime example, we might have in mind the transverse field Ising model with a ferromagnetic Ising term and a transverse field. For small transverse fields, this Hamiltonian is in the spontaneously symmetry broken Ising phase. And for large transverse fields, it's in a symmetric paramagnetic state. And then we know from the Landau theory that there has to be a phase transition between those two phases. And at this phase transition, we have a gap closing. And besides kind of completely understanding this using spontaneous symmetry breaking, we can also write down a local order parameter, right? To just look at the SZ correlations or sigma Z correlations. And this tells us that there's a finite order parameter in the ferromagnetic phase, and this order parameter is 0 in the paramagnetic phase. So this is one case how we can distinguish two phases of matter in 1D. And the other case is...
I'm sorry, can I ask a question?
Sure.
I'm sorry if I'm asking stupid and silly questions, but can you explain again, how do I see that a gap closes?
For this model, it's quite easy because this model can be mapped to, like using a Jordan-Wigner transform, we can map it to a system of like a quadratic model in terms of fermions, and you can solve it exactly along this way. And you see that there's a point in this parameterization, actually at G equals to 1, there's a point where the gap closes. Right? So in the free fermion language, you see that there you can create zero energy excitations. It's zero energy single particle excitations. So for this case, we see this from an exact solution. On very general grounds, if you just only know about the symmetries, we do know that there has to be a singularity in between, but we wouldn't be able to easily predict if it's actually a continuous phase transition or if maybe there's some discontinuity in between or some intermediate phase that we wouldn't know. Here we know it from the exact solution.
Thank you.
Sure thing. So this is one example how we can now distinguish phases or quantum phases in 1D. Let me just come up with the second example, and these are so-called symmetry protected topological phases. And we just use a model that looks almost similar. So now we have a model that has a slightly larger symmetry. It has a Z2 cross Z2 symmetry, and this is a so-called cluster state Hamiltonian. So we have now a sum of the product of SZ, SX, and SZ on the next side. And the second term is the same term as before. This is the transverse field term. Now, again, if we tune in this exactly solvable model, this parameter G, we see that there is again a gap closing. There's again a phase transition at a certain point. However, in this case, both on the left-hand side and the right-hand side of this phase transition, the ground state has the full symmetry. So there is no spontaneous symmetry breaking here. So in this case, we would not be able to distinguish those two phases using spontaneous symmetry breaking. But in this case, the two phases can be understood in so-called symmetry fractionalization. This is a bit of a more abstract concept, which I don't want to explain here in so much detail, but the way that we can identify these two phases is in terms of how the symmetries act on the boundaries of a system. As a consequence of this symmetry fractionalization, we can actually derive a non-local order parameter, and this is a so-called string order parameter. Right? So recall in the example for the spontaneous symmetry breaking model, we had a local order parameter. All we had to do was to measure locally SZ or sigma Z, and that gave us a way to distinguish these two phases. Here, we don't have a local order parameter, but we have this kind of string order. So in particular, if we just take an operator where we apply sigma x on consecutive sites, as shown here, then we can show that this expectation value has to be 0. It's exactly 0 in one phase, and it is finite in the other phase, right? So now again, we have an order parameter, but now it's a non-local order parameter that allows us to distinguish those two phases. Right, and these kind of are now the two different ways how we can distinguish quantum phases in 1D. And what we can do next is that we can just construct a nice toy model where we just combine everything in one model. So we have now the Ising term as before, we have the transverse field term as before, and we have now this so-called cluster state term as before. And if we just tune these parameters on this triangle, so we have a triangle at the corners, we have just simple like fixed points where we have just here only the cluster state term. Here at the lower right, we have only the paramagnetic term. At the top, we have only the ferromagnetic term. And then we can tune through all these different phases and phase transitions. And this parameterization has something quite neat because there's this black line that we see here. And if we go along this black line, we actually can write down the ground state as a simple so-called matrix product state. I'm not going to explain in detail what a matrix product state is, but all I'm telling is that along this path, we have a very nice representation of the exact ground state for this model. Right? Just to biology, like if we go to these fixed points, of course, we just know that there's a very simple way of writing the state. For example, if we just go to the point where we only have this transverse field term, then the ground state is simply just the product state of polarized spins. And here is just the product state, say, of spins up or spins down. But we just have here now a line, and on every point of this line, we can represent the ground state exactly.
Well, what's the maximum bond dimension you need to use?
2. So along, this is a neat property. So basically, if we stay on this black line, everything can be represented exactly in terms of a matrix product state of bond dimension 2.
I see.
Frank, but aren't you crossing a phase transition there?
Yeah, I mean, well, what about the transition point? Okay.
Yes, that's a good point. So at this particular point here, where there is a transition, we can still represent the wave function at this very point, and it has a diverging correlation length. But the way that this bond dimension 2 MPS manages to get a diverging correlation length is that the ground state at this point is a cat state. It's a state of all up plus all downs of this type of state. And in terms of the full model, like if this is a so-called kind of quadratic touching point. So even at this critical point, so this is some sort of workaround how we can now have an MPS crossing a phase transition, and this is because it basically is a non-ejective state at this very point with an infinite correlation length.
Okay, cool, thanks.
But this is also a good question, because if we were to cross slightly lower, like here, for example, then at this very point, we would need an infinite dimensional MPS to represent the state, because along this line, we would actually have a critical point described by a CFT, and that could not be described this way. It's just really fine-tuned to this very point.
So saying somehow the fact that you have a quadratic band touching and goes together with the fact that you have a simple MPS for the...
Yes, exactly. I just going to comment on this. We are now because so what we have here, like this is example that Michael Wolf came up with some years ago, but this kind of generalizes to the entire BD1 class of symmetry. So as I'm gonna mention this as a comment in a moment, but basically we have now a phase diagram of all sorts of different topological phases, and what we can do is we have sort of a skeleton, and if they stay on the bones of the skeleton, then we can just represent. We have like representatives for all phases and for all phase transitions between them in terms of these MPS.
Mm-hmm.
And now coming back to the mission of that because we want to use quantum computers for simulating these systems. And as I pointed out, quantum computers are very limited in their strengths. Basically, they are very limited in terms of the length of the programs that we can have, right? So from classical computers, we can just write programs as long as we like, and they're just going to work, even though they might take a long time. on quantum computers, at least the current quantum computers, we can write long programs, but then on the way the computer forgets what we started from, so that then everything becomes unusable. So we want to do something with very shallow circuits. And this is where this idea of having this simple MPS representation becomes useful, because now every MPS of bond dimension 2 can be represented as this simple circuits. We just have two-side unitaries acting in this staircase way, and then we can just encode the state. And then there's another thing that we use, but I'm not going to comment here on detail, and this is that for matrix product states, we can make use of translation invariance. Right? So we can just use so-called infinite matrix product states, where we bring it into a so-called canonical form, and then we can just represent a state with respect to an infinite system and just do measurements with respect to this infinite state on a certain number of spins. And the same thing we can now do on this, using these kind of sequential circuits. So we just have here like the same matrix over and over, like the same gate over and over, and we just replace the last one with a sort of fixed point gate, which encodes all the information coming from the top. And this way, we can now simulate an infinite system and measure on a finite number of spins as shown here. Right? So for in the simplest case, if we just want to measure a local observable, we just would need 3 qubits. If we want to measure like a string order on several qubits, we just need to use a certain number of qubits here, and where we do the measurements. And all of those gates that we need for representing the state along this path that I just showed, we can just use simple gates that are available on these standard quantum computers. So now we can just use this simple program, or the simple shallow circuit, and prepare the ground state of this Hamiltonian on the machine, right? So now, because of the simple form, we don't have to do a variational optimization, but we can just directly encode the state for certain parameters and then measure the string order. And what we see here is that indeed, depending on what kind of string order we choose, we get the correct answer. And for this model, because it's still sufficiently simple, we can just get the exact answer, and we see that we just approximately getting the right signal. But what we also see here is that the quantum computer is extremely noisy, right? So if the more qubits we take, the signal goes down, which it should not. And the fact that it goes down is due to the noise on this machine. Right? So it just goes down.
Can you go back to the previous slide? I just want to make sure I understood correct. So you're saying that if you want to compute the local expectation value in the state, then I could do that exactly with a finite number of qubits, but I have to choose this green unitary somehow.
Yes, yeah. In fact, in another paper that we wrote together with Andrew, we just use this also as some sort of numerical tool, right? So you can just basically say that you just choose a certain set of these matrices where you just assume that they just repeat over and over again. Like this would be the MPS, which encodes basically the matrix product state. Then you need an iterative way of finding this green one.
So you have to solve for this U1 in order to get it.
Exactly, right? So if you want to, right? So in this case, because we have the exact circuit, we can also just write both the green and the blue ones exactly, and we can just represent it without doing any iterative solving. So we don't need to do any VQE or variation.
That's because you have the state. You're saying you have the exact description of the state.
Exactly. So this is why this is possible.
But for the same reason, this is also a very easy task for a classical computer. Right?
I was just about to say, so what I'm doing here exactly for this reason, that's also extremely easy on a classical computer. So there's nothing that we did here which we can't do with the simplest classical computer, with even like a 50-year-old computer could do this task. However, and this is why I like this idea, is that in principle, if we now, for example, take a state that consists of a circuit which would be the order of not just one layer, but we would maybe have 20 layers, then we would already be beyond what a classical computer can do. So we can now think of a certain subset of states that can be easily represented on a quantum computer, because they would have sort of a low complexity in terms of the gate depth. However, these would be states that can in principle have a lot of entanglement and would be very hard to simulate on a classical computer.
How do we, I mean, with the same idea hold, that suppose I had a few layers of this unitaries, then I could, by measuring and look, if I want to measure local expectation value, I could kind of restrict myself to a subset of the qubits and basically just, you know, take a few layers of the diagram I see here.
Exactly. So what you could do, and this is what we did in another paper where we just call it kind of sequential. So you could just basically just redo, like reapply these kind of staircase maybe 10 times. Then you still have the translation invariant state. And you have very few parameters in this wave function, right? So that would be just the certain number of parameters you have in each of these unitaries. And that would be now a wave function that contains a lot of entanglement. So the entanglement grows linear with the number of gates. And thus the bond dimension would grow exponentially with the number of layers that you apply of these sequential circuits. And that would be now a class of states that you could efficiently simulate on a quantum computer, but not on a classical computer.
But do you know which Hamiltonian?
Just asking whether if I want to compute the local expectation value in this case, I could again restrict myself to a small subset of the qubits, and I could solve for these.
Exactly. So then you just, the number of layers that we need here, sorry, not the number of layers, the number of rows that we would need here corresponds only to the number of qubits that you want to measure, plus a constant number of qubits on top and bottom for the depth. Right? And in each case, it would be the state would be represented in the thermodynamic limit. But this is just one comment. I mean, that directly translates, like this is really a direct analogy to what we're using when we do, for example, infinite this IDMRG or ITBD. Like all these methods are based on the same idea as.
So once you add more layers like this, do you still know which Hamiltonian this corresponds to? Is it the ground state of something that we understand, or is it just a...
Right, so there are two answers to this. So the first, like this is kind of what I'm showing you. We are just writing this up. We're just finishing it, the draft. So we do have a large set of states. So we can just basically write down many states exactly. Right. So we have many states where we just have a prescription, where we can have a path where we find that the ground state of Hamiltonian can be represented exactly in this type. Maybe an analogy to the Laughlin state, right? So we have a specific fine-tuned Hamiltonian to which the Laughlin state is the exact ground state. This is what we can do, but we can also, and this is what we showed in another work, just use this space as a variational space and just use then variation, like some variational method to optimize it. But the variational optimization is still very hard to do actually on quantum computers because of those machines being very noisy. So I think the near term, at least from my view, the near term hope is that we can just come up with certain certain exactly representable states that are still hard to evaluate on classical computers, but easier to evaluate on quantum computers. And as a disclaimer, let me also say that in the beginning, I went through different phases when using the quantum computer. So when we first used this IBM quantum computer, I was just extremely disappointed because my expectation was that, well, it doesn't have that many qubits, but then I felt that those few qubits should have a pretty good fidelity and that we can do whatever we want on these few qubits. But here we see that even using just the order of 7 or so qubits, out of these 20 qubits, most of you just see noise. But the promise is that, and I have no idea which direction it will go, but the promise is that the quality of these gates will improve, and that basically the representable that the time it takes to increase the number of layers that we can add, it doesn't grow exponentially. And by this, that this will be eventually a good way. But to me, this is not obvious that this will be the case, but this is a hope.
Frank, let me add a little bit of info here that for this type of experiments, the dominant noise mechanism on those devices is the measurement noise. To be comparable a little bit, measurement noise can be up to 3%, meaning 97% fidelity, versus the 99.9% fidelity for gates.
Sure.
Yeah.
But one comment on this,
bit,
we see here, like, just by comparing, yeah, right. So, yes, I agree with what you're saying. It's just that still from the experiment, still the noise on the gates is still significant, right? So basically, if you just tried something harder, it didn't really work.
But also, 3% would not get you down from, I don't know what, 0.8 for 3 qubits to basically almost 0 for 5. If it would just be measurement noise, it would be a hit of the order of 3% for each qubit, but somehow it's more than that.
There was a paper like 3 days ago of some group using the Honeywell ion computer, doing something very similar to what you were doing, trying to simulate MPSs. I mean, try to do this kind of the tensors of the MPS using these unitaries. So I was wondering if you looked at it and whether they got better fidelities because they were using different technology.
Good point. I haven't looked at that paper, but there is constant progress, and by now that we just ran these jobs is about 2 years ago. So since then the machines have very improved. Actually, one thing that I want to do is just to redo the same jobs on current devices and see how much they have improved. I haven't done that. But the disclaimer I want to make that in the beginning I was disappointed, but now I'm happy to see that there is any signal at all. So we do see a difference between the two phases, and that's already something, right? So
okay, thank you.
Good. Well, this is all I want to say about this part, and then I want to shift to the second part where we want to discuss, or like where we tried out how to realize topologically ordered states on a quantum computer and how to extract certain hallmarks of topological order from these devices. And I'm following yeah. Okay. So now let me follow a similar strategy. Let me just first discuss some of the properties of these phases, and then show how we can extract this information from quantum computers. So while these symmetry protected topological phases were characterized in terms of properties of string orders and symmetry fractionalization, intrinsic topologically ordered phases are characterized by their emergent excitations, which obey so-called fractional statistics. And because of these sort of non-local quasi-particle excitations, there's a resulting topological entanglement entropy. What this means is we just take the ground state on the plane that's shown here, and we cut out a block, we cut out the circle here, then we would find that to leading order, the entanglement entropy will grow proportionally to the area of this cut, or to the length of this cut. In 2D, this would be like a perimeter law, so it just goes proportional to L. But then there are corrections to this area law, and the corrections are due to some non-local entanglement that we have in this wave function. Right? And this is summarized in this gamma. And this gamma is just intimately linked to these excitations that we have. And for a simple case of so-called a billion anyons, this gamma is simply just the logarithm of the square root of the number of different types of anyons that we have. Right? So this is the first hallmark, that we have non-local entanglement, and we can just extract it from by measuring the entanglement entropy of certain partitions. The second, right, but now it turns out that this topological entanglement entropy is not a unique identifier of a given phase. So we have different topologically orders that would have the same number of a billion anyons. To have a finer classification or characterization of these phases, we actually have to extract the exchange and mutual statistics of these excitations. Right? So the exchange statistics is what we also have for bosons and fermions. If we just exchange two identical particles, we pick up a phase of 0 or 1 for bosons and fermions respectively, and for anyons it could be an arbitrary phase vector. And mutual statistics we get by just moving one anyon A around another anyon B, and we just have to check what kind of phase we pick up. Right? So these are now quantities that we can use to characterize topological order. So now we follow again a very similar strategy what we did before. Extracting this for a general Hamiltonian would be extremely hard, because then we would just have the first task that we would have to do is to, for example, variationally minimize the energy. So we just choose here a simple toy model. In this case, the Tori-Code Hamiltonian, which is the one shown here, consists of terms, like a sum of terms over these stars. So we just having here the product of sigma z's on these blue stars, and the sum over all stars, sum over all vertices, and we sum over all of those star terms. And we have another term, which is a plaquette term, where we have a product of sigma x's on the red plaquettes, and then we have a sum over all of these plaquettes. The neat thing about this Hamiltonian is that all terms in this Hamiltonian commute, and thus we find it easy to solve it. Particularly, we can solve it individually for all of those terms. And let us start first by solving or finding the ground state for the vertex term, or like for the term of these on these stars. And we find that in the ground state, all stars have an even number of spins pointing up and an even number of spins pointing down in the Z basis. And there's a nice graphical representation of this. We can say that, well, whenever we have a spin -1, say, we draw a loop segment, or we just draw a thick black line on that particular bond where we have a spin down, and we just leave it blank when we have a spin up. And then this constraint that we get for the ground state, namely that there's an even number of spins up and an even number of spin downs, translates into a simple rule of having only closed loops drawn on this lattice. Right? So that's fairly easy to solve. So we just take our lattice and we just draw any pattern of closed loops, and that's going to be a ground state of the first term. The second term, or to minimize the second term, then demands that we take an equal-weighted superposition of all of those loop configurations that we can draw on this lattice, and that's then the ground state. And there's a lot to say about this ground state, and this ground state having a different degeneracy when putting it on a torus versus putting it on a sphere, etc. But for right now, all I want to keep in mind is that we have a fairly simple prescription for the ground state, namely that the ground state is just given by an equal-weighted superposition of all loop coverings, and that's it for now. And this state then has a so-called Z2 topological order, and it's also easy to identify what the excitations are on top of this ground state, namely these can either be no excitation, it can be an excitation of plaquette terms, which we call like the magnetic particles, it can be an excitation of the vertex term that we call electric particles, or it can be a combination of two of those defects. So this is now characterizing this topological order found in the toric code model. Now, going back to the quantum computer, now in a similar spirit to what we had before, we don't want to variationally solve the problem, but instead we have now a state that's simple enough where we have a prescription how to generate it. And to read these pictures that I'm going to show, a few of them, I just want to take a little bit of time to just discuss this picture here. So we have this square lattice shown in black, and this is the same lattice as before. And we have the spin degrees of freedom living on the bonds, right? So as shown here. So the qubits are now the circles that we have. And then we have two different, like we have the plaquette terms, which are the ones here, right? So we have 4 qubits around the plaquette, and we have 4 qubits around those stars. And now we can take the initial state on a quantum computer, which is the state where all spins are set into the SC equals to 0 eigenstate, or like SC equals to +1 eigenstate, whatnot. So we have just a very simple polarized state. And for that state, we see that all of the vertex terms are in the ground state, right? So all of these vertex terms have an even parity, and the product of them is +1. This is exactly what we want for the ground state. The plaquette term, however, is in a SX equals to 0 state. So this is not corresponding to what we want for the toric code ground state. And what we then did is we just were knowing what the quantum computer can do efficiently and how it can do it efficiently, namely it can apply C0 faster than others and entangling gates, and it can do stuff in parallel. So on, we thought about a sequence of gates to apply such that once we ran our program, that we get the proper toric code ground state. And the way that we do this is we just apply Hadamard gates to a subset of those spins, and then we sequentially apply C0 gates onto the system as shown here. And if we just follow the right sequence, then we see that once we are done with our program, that we are left with the toric code ground state, right? We see that now all the vertex terms are in the +1 eigenstate, and all the plaquette term are in a parity 1 eigenstate, in this case for sigma x, right? So now we have a relatively short program, the order of a few dozens layer of gates that we can apply, that we can create the toric code ground state.
Right. In principle, the depth of the circuit would have to grow with the number of qubits, wouldn't it?
This is correct. So I was just about to point out, so when using unitary gates on our system, then the depth of the circuit grows linear with system size, or linear with the linear system size with the width of the system, right? So because what we have to zip across the system, and this is now similar to the state that we had before, so that we have to just do a sequential application of these gates through the system. And this is right. So this we know has to be the case for these kind of wave function because they are topologically ordered. So we have this long range entanglement. So we need, if we just use unitaries to create the state, then the number of gates or the gate depth necessarily has to increase with system size.
An alternative could have been to measure the stabilizers and then maybe apply corrections, but probably this is not so good because the measurement is not so good as was mentioned before.
Right. So this is now right. So this is correct. So here we just focus on the case where we just use only unitary gates that we know how to apply on this machine. If as you say that if we just take this state here and we would just do measurements on X, we could just prepare the state at constant depth if we do measurements, but that for technical reasons is indeed harder here. So at this point, I wouldn't claim that this is the best way to create the toric code. This the best way that we found for the architecture on the Google quantum processor. Applying this now to the machine, we can then measure separately the fidelity on each of these plaquettes and stars, and we see that we get an average stabilizer fidelity of about 90%, which we were quite happy with to see. So now, using this sequence, we have now created the ground state of the toric code, and now we can play with it. So now we can just do measurements on this using the machine. And as a first test, we then want to extract from the state that we have prepared the topological entanglement entropy. So this is the...
Sorry, I'm just wondering about the geometry. Should I think of, so are you preparing the ground state as like equivalently in a torus, or should I think of a strip geometry? I mean,
Right.
you have like long-range gates that are actually forming it, making it form a torus, or...
Right, thanks for the question. So at this moment, I just don't want, I just want to kind of get the ground state for some system, and what we do here is we just fix the boundary, such that for the fixed boundary would have a unique ground state. Right?
Okay.
But I'm coming back to the geometry in a moment.
Okay.
Can you explain what do you mean by average stabilizer fidelity?
Oh, by the average, we just mean that we just look at the fidelity of, so we can just, so each of these plaquettes or vertices has an overlap, on average an overlap of 0.95 with the exact state.
Wow. Okay. Okay.
So this is measured experimentally, yes?
Yes. So these are just measured experimentally by measuring, then doing measurements on the plaquettes and on the vertices.
Okay, and the code that you used, so is this developed manually, or is there a compiler that you use somehow to reach an optimal code?
Right, the way it worked for this is that we just use Circ to just develop this code, right? So we just use Circ to apply this specific gate sequence and so on. Right, and this is written code, and there's a certain fine-tuning basically about how to put this on the chip, etc., which was then optimized. Does this answer your question?
Yes, yeah.
And in practice, how it works, so Leo, the student in our group, mostly wrote a Circ code, and then probably it was like tweaked by Kevin for the exact geometry, but that I don't know. Good. So now we have the state with a pretty high fidelity, and now we just do measurements on that. And the first measurement that we do is to measure the topological entanglement entropy. And for this, we use this subtraction scheme proposed by Kitaev and Preskill. And from this, using this subtraction scheme, we can then, the area law terms and boundary terms will cancel, and the only thing that's left is this topological entanglement entropy, which for the specific type of toric code, where we have four different types of abelian anyons, should be log 2, right? So the correction, the area log correction should be then minus log 2. And that should be independent of what kind of cut we do. And so we just tried out several that we could accommodate on the chip, and we just move it around on the chip to do some averaging or to get some distribution of measurements. And for small geometries up to 6 qubits, this can be done using full state tomography, which means that really all elements of the reduced density matrix are measured. And for larger ones, we use randomized measurements to extract the so-called Renyi entropies. Right? And one property of this topological entanglement entropy is that it's actually the same for all Renyi entropies. So we can just use any entropy, and we're just using the Renyi entropy of index 2. And well, we can do some statistics of this, but the upshot, and this is the main panel to look at, is the one shown here in green, where we now, for the different subtraction schemes, see that the value is pretty close around the expected log 2. Right? And that I was quite happy about, because it shows that indeed the ground states that we prepare has a correct contributions to the area law, and it's independent of geometry and size of the partitions that we use. So this kind of shows the first sort of hallmark of topological order. And secondly,
why do you use the Renyi entropy? I mean, you have the density matrix. Why don't you just?
Well, we do, right, but we also use other entropies. So the reason that we use Renyi entropies is because for the largest cluster, for the one with 9 qubits, we cannot do state tomography. So we want to just compare apples to apples, basically, and that's why we just use the Renyi entropies. However, for the smaller ones, indeed, we just calculated different entropies, and we find that the area log correction doesn't vary much compared to the noise that we have. Right, so there are slight differences in the numerical value that we get for Neumann entropy as compared to the Renyi entropy too, but that's not a big deal difference. And in for the exact solution, if this was a perfect quantum computer, there shouldn't be any difference. It should be exactly log 2 for any entropy.
Okay.
So let me now come to the last part, where I want to now directly measure the exchange and mutual statistics. As I pointed out, that to characterize topological order, the entanglement entropy is not sufficient. So we also want to look at the actual statistics of these particles. This can be summarized in the U and the S matrix. So the U matrix is a diagonal matrix containing the phase that we pick up when exchanging two particles. And the S matrix is now a matrix containing the elements that we get, or the phases that we get when moving an A particle around a B particle. Now, once we have created the ground state, what we can then do is we can now exactly create these particles. So for example, if we apply a string of sigma z's to our ground state, then we see that at the end of a string, we will create M excitation. So this is now a plaquette excitation. The other one we can basically shift to infinity, and we can create an E excitation by applying a string of x's. And now we can just apply a sequence of X operators to move this E particle around the M particle. Right? So now basically we have the advantage, instead of actually doing some adiabatic movement of the particles around each other, here we know exactly what these operators boil down to. So we can do this again with a very low depth circuit. Like, so we just need to apply these local circuits. These kind of a sequence of single side gates. And the way that we can then extract the phase is in the following way. So we now introduce some extra qubit to our system, right? So we have now our system, and the system doesn't eat up all the qubits that we have on the chip. So we now take some extra qubit. And then we just prepare a state, which is now the superposition of our initial state times 0 plus our initial state times spin 1. Right? So this is now a superposition of those two states. And then we applied a control U operation. So basically, in one copy of the system, nothing is happening. So the particles just sit where they were. And in the other copy, the system do abrade. And then we can, by calculating the overlap of those two spin states, we can then extract the phase. So it's a Ramsey interferometry, and this was proposed by the Zoller group some years ago. So now we can apply this idea to our ground state, on top of which we created all sorts of excitations. So we can create, for example, two electric particle, like two E excitations, and then move them, like exchange them, and then measure the phase. And we see that for exchanging two E particles, we get a phase of roughly +1. And if we exchange two M particles, we also get a phase of +1. If, however, we are now exchanging a bound state of an E and an M particle, that together makes a fermion, we see that indeed we get a phase of -1, which is shown here. And these constitute then the elements of our U matrix, and we can then also move around E particles, around M particles, and vice versa, and then get all the elements that make up the S matrix, right? And then with this, we can now extract all the different phase factors that we need to characterize this kind of topological order.
This is very impressive in the sense that if you condition all your circuit on this single qubit, then your actual circuit must be extremely high depth, no? I mean, because you need to have a lot of swaps in order to control every gate of the U on this particular.
No, but these are local moves. See, they're moving this anion locally.
Yeah, but they are all conditioned on a qubit, on a specific qubit, no?
Yes, but this, right, so there are a bunch of swaps, but this still works on that machine, right? So there are a bunch of these kind of swap gates, as you say, to relate it to this one, but that it's still doable.
Well, what is the depth of the circuit in that case?
I think, sorry, the exact number I forget. It's maybe the order of 50 or so qubits, 50 or so layers. I mean, many of them can be applied in parallel, which helped. Mm-hmm. And there a lot of thought went into it because these machines are very good in applying gates in parallel. Yeah. So we can try to come up with circuits that do as much as possible in parallel.
Okay, thanks.
How do you control that? I mean, there is a phase you accumulate just to energy.
Well, this part we don't have, right? Because we just really know the actual. So here, so you say that, well, we get a dynamical phase and
the dynamical phase, and you're applying some Hamiltonian to.
But we don't. This is the thing. So we just know. This is why this case is particularly easy, because we know exactly this part that we just get by applying these sigma x's, right? So here the Hamiltonian is set to 0 for this. This is maybe a good important point to make while we just extract, or we just properly kind of simulate the braiding, these are not properly protected qubits, right? So these are not protected by any energy gap. We don't have a Hamiltonian here. We just basically, we just rely on being very careful on telling the machine what to do. There's no protection by any energy gap here.
Yeah, I'm just thinking whether you have to also control somehow, basically what I'm saying is the result here depends on the dynamical phase you accumulate when you apply each one of the gates.
Yes, but we don't have this.
How do you know? You're applying a non-zero, you're applying a Hamiltonian to apply the gate. So
But these gates, we just apply sigma x operation to the system based on our.
Yeah, sigma x.
Or you mean like the way how it's implemented in the machine?
Yeah, the sigma x could be multiplied by some global phase factor, which depends on, it's a dynamical phase. Nobody cares about it usually. You only start caring about it when you do these comparisons. And
this is right, but this phase is I mean, right, so now in a way you asked me a question that I can't really answer because I don't know exactly how this is implemented, but this is under control. So they know exactly this dynamical phase is known to the machine apparently, but I can't give you any details because the way that Kevin basically implemented this is in a way that he just knows exactly how to get rid of those phases. So the way that we think about there is indeed that, well, we just apply, like on a piece of paper, that what we would do, that we just apply these sigma x operators and don't worry about the dynamical phase.
Okay. Yeah.
So let me just close by just saying that, well, we just also then experimented with towards sort of logical qubits, where we now change the boundary conditions by having these kind of non-local boundaries, that it effectively our system lives on a torus, and in that case we have a finite ground space in which we can then encode topological qubits, right? So we can then have a topological qubits, and we have this sort of state injection, so that we have a sequence that we apply to prepare a state in a certain topological ground state, like a degenerate ground state, and then we can see that we can then read it out and we get a stable representation of a topological qubit. And as an outlook, I mean, one thing that we are now working on is to generalize this idea that I showed for the toric code to arbitrary string nets. Right? So we can, for example, now write down the ground state of some Fibonacci anyon string net model, where we then have where we can then also braid non-abelian anyons. On paper this works, and it still has a rather finite number of gates, but it's beyond what we can do on current machines, but it's off by a factor of maybe 5 or something like this on what we can achieve. So the hope would be that if the machines keep improving, that we could then also simulate non-abelian anyons and braiding on these machines. So let me now come to a close and thank again my collaborators on this project, and thank you for your attention.
All right, thanks a lot. So Frank, you maybe a provocative question, but can we conclude from this that the Google machine is better than the IBM machine?
Well, this is my current judgment, but actually just since yesterday I didn't have an IBM account for a while, but since yesterday I have an IBM account again, and now I want to see if the new machines in IBM have actually significantly improved. And that's why now actually I want to redo these experiments that we did 2 years ago and see how much better it looks like. I mean, honestly, I just looked into it yesterday, just before signing into the seminar. So the new IBM chips include one that has 65 qubits, and in terms of the numbers, it looks really good, but I haven't played around with it yet, so I don't know. And one thing also, the chip that we used is still this Sycamore chip. It's exactly the chip that was used for these quantum supremacy experiments. And I don't know what the evolution is also at Google, because that chip is also already several years old. So probably they have also something better already in their back offices, which I don't know about.
Other questions?
So maybe another slightly provocative one, right? In Israel, we were recently asked if we want to apply for money for cloud time on quantum computers.
Mm-hmm.
So obviously we could do that to investigate quantum computers, but do you think there are examples now or coming soon where we can use that to answer physics questions more efficiently than classical computers? Or how close are we to that?
So we are working on, right, so we're having also other projects. We are now trying to come up with specific problems where this is like what I discussed in the very beginning. We're saying that we want to identify problems that are hard on classical computers, but somewhat easy on these machines. And in a very kind of simple way of thinking, we could say that, well, the best we could do is on a classical computer is maybe matrix product states, like just to compress the data. And then we can just say that, well, matrix product states on big computers, we can do maybe with the order of a Bond dimension of 10,000 or so. And if we then translate this into the number of gates, because that can be directly translated into the gate depth. And this is something that we probably reach fairly soon, right? So for these stuff that we did on the Google machine, so the number of the gates depth is already getting where it would be hard for MPS simulations. So, and I think it really depends on the scaling. If basically they progress at this pace, if they progress at the pace that the circuit volume has increased over the last few years, if this keeps going on, probably we are fairly soon in a regime where it will be hard for classical computers and easy for quantum computers. Okay, but cool. I mean, since I don't know the hardware well enough, so I don't know what the perspectives are on this. But I think it's good to have access to these machines, because from playing around with them, we see what their strengths and weaknesses are, and then we can just be prepared. But if there's this chance that there will be very powerful machines, it's good actually to know how to use them. And yeah.
Do you have any similar scheme to the one that you use with the matrix product state to use PEPs, for example, or other 2D kind of network where, you know, yes, quantum advantage might be much more obvious in yes, some.
Yes, good point. So in a basically, well, I just originally not related work together with Mike Zaletel. What we did is we explored a subset of PEPs, like a set that we call so-called isometric tensor networks. Right? So basically, in the space of PEPs, there's a certain subclass of PEPs which are, in a way, an analogy to matrix product states in the canonical form. And those PEPs can be directly translated into sequential circuits in a similar way to what we are doing here, right? So there's a subset of these states which can be applied in a sequential way, but then it's not just a linear way, but we would just maybe start from a corner and just apply then a sequence of for example, unitaries acting on plaquettes. And in fact, what we showed was that all stringnet models, etc., can be directly represented in terms of these isometric tensor networks. And that was actually the first thought, like the starting thought for this Google project, where we first used this analogy. We first wrote down the isometric tensor network, and then we wrote it in terms of a gate sequence. But it turned out that this gate sequence was also scaling linear in system size, but the one that we found here was more efficient.
But the fact that they are isometric doesn't also mean that you have an efficient classical algorithm for contracting them?
We do have an efficient classical way of contracting them for certain parts. But the thing is that it depends on what you want to measure. So this tensor network itself can be efficiently contracted. This is why we came up with this at that time. However, it really depends on what you want to measure. If, for example, if I just give you an isometric tensor network state and ask you what is the topological entanglement entropy, that would not be easy to extract.
So if the